Yeah, go ahead. So I'm going to talk about Elastic, the models, and a bit about how the simulation works. So go ahead to the next slide. So just to motivate things, a few years ago, we ran a public 25K Kaggle challenge to photometrically classify 3 million transient light curves in the LSST passbands. So that included 18 models and a magnitude limited training set that was roughly based on the expected performance of Foremost. It was a joint effort between two science collaborations, DESC and TVS. And the primary goal was to motivate machine learning classification, but it was also to improve the simulation infrastructure. And below is just a chart showing the relative fractions of each transient type, which is in Renee's results paper. Next slide. So to the extent of motivating classification, I think we succeeded based on this list or partial list of classifiers that have been used or have been developed using plastic data. I'm not going to go through them. I just wanted to show the big laundry list of classifiers under development using plastic. Next slide. So from plastic 4 years ago, we are now working on ELAsTiCC, which is essentially a broker test. And so the goals are to test the alert infrastructure, sending, receiving, processing, all that under the hood stuff. That's really important. We want to test this with reasonably high volume. So it's about 40 million alerts over 3 months. Of course, in practice, 40 million alerts is like a week, but we're going to distribute over 3 months. And to test classification algorithms on transients plus their host correlations. And then in parallel, there's a lot of synergistic development for simulation and analysis going on. Next slide. So I wanted to point out that what this simulation is really for and how it's being used. So that this is an SNN simulation, and the primary reason for its existence and development is for an SN1A cosmology analysis. And in particular, there are 3 things that we need it for. We do distance bias corrections, training classifiers, and using beams. So roughly speaking, you can think of the simulation as 2 parts. First, there's the physical universe. We want to model type 1A and non-SN1A contamination. Now, of course, contamination to us in a cosmology analysis is always somebody else's gold, so you have to be a little careful about the language. And we want to model host galaxy properties and their associations. Then we want to connect the light coming from these sources to the instrument that's looking at it. So we want to model the host galaxy effects on observations. We want to model cadence and observation properties, noise, and survey selection effects, which we often refer to as a trigger. Next slide. So here's kind of a cartoon of how the simulation works. You can think of it as 3 parts. First, there's an underlying source, an SED source. And then that light from the source travels through the expanding universe, goes through some dust, and eventually goes through a filter in your telescope. Then there's the noise model that says, well, this is what the instrument reports, some flux and ADUs or photoelectrons with some fluctuations. And then finally, on the right, there's some trigger model. And for LSST, for example, it's a single detection. I'll show you a bit more what the trigger model is later. Usually it's 2 detections. LSST is rather bold, triggering on a single detection. We'll see how well that works. Next slide, please. Let's see. There we go. It's worth pointing out some simulation improvements because of plastic and elastic, and I was anticipating improvements, which is why I got involved, even though plastic and elastic are not cosmology analyses. I thought there was a lot of synergistic overlap where everyone would benefit. So for example, peculiar SN1A are now a standard part of our contamination that we use for training classifiers and using for beams. So it's actually part of our SN1A analysis now. We have transient host associations. You can thank Martine Loken and the organizer of this session for doing an incredible amount of work and effort to make that feasible. We now have PhotoZs. A PhotoZ, I should have said PhotoZ PDF instead of point estimates, thanks to Alex Maltz and company. We also have a light curve library to model galactic transients, something that we didn't have prior to plastic. And AGN are actually a contaminant for SN1A cosmology, so I'm eager for the day when somebody provides a good enough AGN model to actually model that contamination. Also, because of plastic and elastic, the simulation is much more robust to community model input, and it's much more robust to large jobs. So I remember 4 years ago trying to simulate all of wide, fast, deep, and needless to say, it didn't work. But now it's really trivial to generate 30 models in the whole wide, fast, deep overnight on 40 cores. I mean the whole thing, not some pre-scaled subset. Next slide, please. So as far as the models in SNANA, there are different classes of models. I don't mean Python classes, they're like conceptual classes. So the first one is parametric, and SN1A are really, for now, basically the only parametric model. It's well defined by its color and stretch. There's something called a non-1A SED, which is an SED time series derived from real data. So if you have, 30 or 40 very well measured, core collapse light curves plus some spectra, you can kind of splice together an SED model. And Maria Vincenzi has done a lot of recent work improving these models. The next class is called SIM-SED. It's kind of a dumb name, but it's really intended to be a time series from theory models. It can also be from data, but it's more useful for more exotic things like kilonova and TDE or superluminous supernova. And the idea here is you can have the SED time series dependent on things like ejecta mass, lanthanides, and so on. And the original goal of this model, where I was working with the Flash Center at Chicago, was to sort of find the distribution of physical parameters that matched the data. But we weren't able to create enough models. They were just too expensive. So that never really panned out. But maybe someday that can. And of course, many codes can generate theory models, but the nice thing about SNN is it includes all the survey selection effects. So you can start with your underlying theory model and then produce what you would actually observe. And then lastly, as I mentioned before, there's this light curve library for galactic transients, both recurring and non-recurring. All right, I'll pause for questions. Does anyone? I can't see if there's a question, but. Okay, next slide.
Rick, this is Douglas Tucker. Just a quick question. Do you have any kilonova models in the, and if so, from which, and if so, what set of kilonova models do you use?
So in the original plastic, we used the Kaysen 2017 kilonova models, and some more have been added, but that's all I'm going to say.
Other questions?
I think we can add a little bit more detail. So the other set of models are...
Wait.
Oh, is this mic working? Yeah. So the other set of kilonova models are from Bulla et al. And the other thing we've done is you can simulate not just the optical light curve, but we're also simulating LIGO, Virgo, Kagra alerts. So for example, if you were in the DAS GW spectroscopic follow-up team, as I know you are, this is a useful test set.
Oh, yeah, good point. I forgot about the sky maps.
Awesome. No other questions in person. Rick, you were smart to go remote. We have a flash flood warning here in Tucson. Do we have any questions in the chat, Alex?
I hope you guys are on a high floor.
No blue jeans questions. Okay, feel free to continue, Rick.
Okay, next slide. So here's a list of all the models. And so on the left are the extragalactic models. They're mostly supernova. And on the right are the galactic models. And of course, the galactic models, there are plenty more, but this is at least the models that were contributed. So on the left, the extragalactic models have pretty good rate models to go with them. And so we expect those to represent, the physical universe. On the right, I think maybe one or two have a decent rate model. The rest, we just made up a number, some reasonable number of events to generate. So don't expect all those to have the physical rate in ELAsTiC. And then I've also indicated a lot of contributors, students, graduate students and undergraduates who contributed to these newer ELAsTiC models. Okay, next slide. So now I want to move on to some simulations, how the simulation works a little bit. So for simulating the host galaxy, the basic idea is it reads a host lib or host library, which is a catalog of galaxies, either real or theoretical, and their properties. And there's also a weight map, which gives the probability as a function of those properties that the transient resides, in each host. So for example, a supernova core collapse has a much higher probability in a star-forming galaxy than, an old red galaxy. So the weight map would encode that information. And thanks to Alex and Martine, we have weight maps for many, I think most or all of the transients instead of only for a few supernova cases. Next slide. So in the original PLAsTiC, the host properties were rather limited. It was, these three items. And we knew it wasn't very good and not very realistic, but we just sort of grit our teeth and carried on because you have to start somewhere. Next slide, please. So now we are at a happier place with our host properties. We have a PhotoZ PDF. We have a Sersic profile. So we put transients, on the galaxy according to the profile. It means we can measure a separation. We can also measure what's called a distance light radius and apply matching criteria. And so in this challenge, the number of matches will be mostly 1, but sometimes there will be 0 matches and sometimes there will be 2 matches. That's reality, and the brokers hopefully will figure out how to deal with that. There's also properties, mass, star formation, and color. And these are used under the hood to assign the host based on the transient host correlation. So that's the underlying, physics there. And then there's also a local surface brightness, which we use to anomalously increase the flux scatter. It's something we've observed in both DES and with DC2. And so that effect is in there as well. So basically, nearby, like a kilonova on a bright galaxy, the flux will scatter a bit more than Poisson noise, actually quite a bit more. Next slide, please. So just to show what this flux scatter effect does, this is a plot. And the vertical axis I put in words to the left. It's the actual scatter divided by what you would expect from Poisson noise. And you can see at bright surface brightness, like 20 magnitude per arcsecond squared, the actual scatter is more than double what you'd expect from Poisson noise. And we still haven't quite figured out how to fix that. Okay, next slide. As far as the depth, the plan for now is in year 1 of the challenge, it will be the depth of the galaxies will be based on a 2-week co-added depth. And then in years 2 and 3, It will be based on a 1-year co-added depth. So that will impact the fraction of hostless galaxies. Now, I don't know the real timeline for getting a 1-year co-add or a 6-month co-add. This is just a rather arbitrary. If people really feel strongly that this is woefully wrong and have a better model for the depth versus time, I'm happy to implement that. All the photo-Zs, however, are based on a 1-year depth. It's really a coding practicality. It's a bit more difficult to have the photo-Z depth varying in the challenge. Okay. For the cadence, it's based on OpSim, but SNN simulation doesn't read OpSim. There's a translator that translates the cadence. And the idea is we pick 50,000 random sky locations over the wide, fast, deep area. And for each location, we sort of drill through and identify every observation and record the image properties, essentially, which are listed in brown. And then using the model magnitude at each MJD, the sim computes the observed flux and the uncertainty. Now, of course, with 50,000 locations, we're generating over 100 million events. There would be a lot of duplicate RA and DEC locations. So we shift the coordinates to a random location within a small radius so that you don't get duplicate RA DEC locations. There's no large-scale structure, so don't try to look for that. And the selected host from the host library is just moved to this random location. So the galaxies are representative, but we don't literally use their coordinates. Okay, next slide. So redshift, we select the CMB frame redshift from an appropriate model. We transform to heliocentric, and we pick a random peculiar velocity. Again, no bulk flow correction, so studies of sigma 8 and things like that won't work here. Next slide. For the noise model, it's in the circled with the orange line. So there's a source, the source itself contributes some noise, but most of the noise typically is from the background sky, which is B times the noise equivalent area. There's also a Poisson noise from the host. And then this S_sim, that's the anomalous noise from bright galaxies. It's empirically observed. We don't really quite understand why it's there. And this comes from DC2, studying DC2. Next slide. So this is the trigger model. It's a single detection, and it's based on how DIA performed with DC2. So this is the efficiency for detecting as a function of signal to noise. And a good way to characterize it is at 50% efficiency, the signal to noise is 5.8. But it's not an exact step, it's a curve. Okay, next slide. See, I was asked to show what is in the training sample and alerts, so it's a bit detailed to discuss here, but there is a website that has that detailed information about exactly what is there and the variable names. Next slide. Okay, the schedule. So the training sample, which is really only to train classifiers, was released back in May. And there's been a few updates with bug fixes, so thank you everyone who noticed and reported those bugs. It's FITS format, it's publicly available, but it's there just to train classifiers. It's not to grease the wheels of the brokers. For the brokers, we have a 10% alert sample. It's an Avro format, and it's being restreamed to the brokers every 2 weeks, starting from mid-June, and will continue through mid-September. And Rob can give you more details about that. But the idea is that the broker teams can keep debugging their infrastructure, and if they're on vacation, they can come back later and debug it We also did a full 100% test generation in late July to make sure we could do it. We generated the full sim, translated everything to alerts, and loaded the TOM database. So this stuff in green was really all just sort of debugging and getting ready for the challenge. So the idea is in mid-September, we plan to start streaming the full 100% sample. And that will continue essentially until Christmas, mid-December this year. There will be a little over 4 million events and more than 40 million alerts streamed over that time. It's about 90 gigabytes compressed, so it will be several hundred gigabytes uncompressed. And depending on how things go, we might restream again in the winter of next year if people feel like they didn't have things debugged well enough and they want another chance. And that's all I have.
Great. Thanks, Rick. Could we maybe get one question if we have it, and then we'll save the rest for the discussion at the very end, if there are more. Okay, Alex, any in the chat?
No online questions yet. If you have
Great.
any, please put them in the document. We'll get to them.
Awesome. Okay, so moving right along, thanks, Rick, again. We heard a little bit about what it was like to simulate alerts. Now we're going to hear a little bit about what it's like to generate real ones from Melissa Graham.
Okay. Yeah, so Alex and Alex suggested I could come and tell you a little bit about the data products for time domain astronomy, and in particular, exactly what's going to be in the alert packet. So my name is Melissa Graham, and I work for the data management team as a science analyst. So that's the context for me being here and telling you about what's in the alerts. But let's take it back a step and kind of just talk about all of the LSST data products in general to have some context for the alerts. So as you may have learned yesterday, if you were in the intro to Rubin session, or as many of you already know, as the raw data comes off the telescope, one image every 30 seconds, it gets processed by our prompt processing pipeline, also known as alert production or the AP pipeline. And what happens to it, it first undergoes instrument signature removal, so the standard standard reduction and calibration. And then it undergoes difference image analysis. The short form is DIA, and that's where you subtract a template image that was made from images obtained, say, the year before. You subtract it from the new image to make a difference image. Then you run source detection, characterization, and measurement on that difference image. So you have a bunch of sources you've detected in the difference image. We call them DIA sources, difference image analysis sources. And every one of those that we detect with a signal to noise ratio greater than 5 triggers an alert. An alert is it's basically just a little ASCII file or packet, we'll call it, and it's just full of all the information that LSST knows about that thing that it just measured. So it knows like coordinates, flux, that kind of thing. Those packets of the alerts go to what we call community alert brokers. Those are sort of independent software systems that are being developed specifically to deal with this flow of alerts, flow of these millions of alerts per night, to sort through them, filter them, and make them available for users who want to do real-time science. So as someone interested in doing science in real time with Rubin Observatory, it's really the brokers that you're going to be interacting with to use the alerts that are made. And those are things like Antares and LSST and other brokers. I don't really have slides about the brokers. But that's what an alert is. That's how it gets made. There are other kinds of prompt products that Rubin Observatory will make as well. So, and within 24 hours, basically, what we call the prompt products database gets updated with all of the detections from the night before. So that's the same data that has gone out in alerts, but it's in catalog format. So you could log in to the Rubin Science platform, for example, and whatever cadence suits your science schedule, daily, weekly, monthly, whatever, and you can be querying those data products in the prompt products database to see, if you can find anything that's risen by X magnitudes over X days in your favorite filter, or whatever the thing is that you're interested in finding. So you can also query the prompt products database that way. The other time scale that we sort of work on, so there's the prompt data products, 60 seconds, 24 hours, but then there's also the yearly data releases. Every year, all of the data that was ever taken by Rubin Observatory gets reprocessed, so that every image is re-reduced. All of the difference image analysis is redone. So even at year 6, you're redoing all of it with the latest versions of the LSST science pipelines. And you're also restacking all of the data to make very deep coads, and all of that comes out on a yearly basis. So if your interest in transient-related science is more like rates, occurrence rates, population studies, that kind of thing, you're not necessarily needing to use the alerts. In that case, you might actually be more interested in using the annual data products that also have the DIA in them to go through, find your giant populations of things, and do it that way. So that's kind of a broad overview of all the different types of LSST data products for transient science, and that's how alerts fits in. The other way that alerts are different is that they are a world public data product. Everything else that Rubin Observatory creates has a 2-year proprietary period, and also the Rubin Science platform is proprietary to data rights holders, which is everyone working in the US and Chile and named members of international teams. So it's still like 7,000 to 10,000 astronomers worldwide, but still there is that threshold of being a data rights holders, whereas the alerts are world public. They can be shared anywhere with anyone. So that's some context for alerts. So I wanted to just pick out now, even in a little more finer detail, data products that are useful for time domain astronomy. So and really give you some of the nomenclature as well. So we have processed visit images, also called PVIs, also called direct images or single visit image. I haven't got them something. Yes, we have lots of names. They're also called CALEX. So there's so many names for these. It's just the single visit that was obtained of a single area of sky at a time in a filter. So those are the PVIs. Then we have the difference images that we just talked about, the template images, and the deeply co-added images. So the first 3 are sort of obvious how they relate to time domain data products, but I've included those deeply co-added images in this list because that's where you get the host galaxy and the populations from, so the context for your transient of interest. So those are the image data products that we would expect you to be using for transient science. Then there's the catalog data products, which I just spoke of too, the DIA source. Then there's also DIA object, where you have the source, which is add detection in a difference image at a certain time in a certain filter. But the DIA objects are associations of DIA sources. So that's at a certain location of sky where you've seen multiple DIA sources appear. We collect those together, and they're stored as a DIA object. And then there's additional measurements and characterization of the object that have to do with the light curve. So you have some sort of easy to measure light curve parameters for that DIA object, like the peak observed brightness or peak observed flux. That's a really obvious one. And some other things about like amplitude of the light curve, things that are easy to measure are all in the DIA object. There will also be a DIA forced source catalog where force photometry is done on the difference image at the location of every DIA object. So you might have a variable where only sometimes it becomes a DIA source, because only sometimes we can detect it at signal to noise ratio greater than 5. But you want force photometry when it goes below that. So in that case, you're using the DIA forced source catalog. The fourth catalog that I've included here as relevant for transient science is the object catalog, because those are the detections on the deeply co-added images. So that's where you're getting your host galaxy brightness, size, color, shape, all that kind of stuff is coming from the object catalog. And then, of course, down at the bottom here, I have the alerts, which is the data product we just talked about as relevant for time-domain astronomy. So I want to dig just a little bit deeper into what exactly, like what are the measurements in the alert that you will have access to. So within that DIA source record, and that's the thing that triggered the alert to happen in the first place, you get things like a unique identifier, which filter it was, which program that image was obtained under, whether it was wide, fast, deep, or deep drilling field, basically, or a TOO. That should be in there as well. You get the mid-exposure time, the time at mid-exposure, a centroid, so the coordinates, calibrated fluxes of a variety of types, so PSF, aperture, etc. You have some shape measurements, like whether it's trail or dipole. If you were in the DIA session earlier, there's that kind of information. The signal-to-noise ratio, and then, of course, a spuriousness parameter, which is like a real bogus parameter that helps you make cuts on things. And also that will be provided will be like what spuriousness cut you should apply if you want a completeness of X or a purity of X in your sample. So that kind of characterization of the real bogus should be done for you as well, so that you can make cuts not just on flux, but also on the real bogus / spuriousness parameter. Also within the alert packet, of course, you have the DIA source, which triggered it, the DIA object that it was associated with, and all of the DIA sources that are associated with that DIA object, which is just the complicated way to say you have the light curve, basically. So you have like a 12-month history of everything at that location in the sky as well. And what else did I want to tell you? Yeah, so that alert record also includes if there's a history of forced sources. So if we saw it and then it went below detection threshold and then it came back, those forced sources are also included in the alert. So it's in that history. And right, so there's the situation where you have no history. It's a completely new DIA source. Nothing has ever been detected at that location before. It becomes its own DIA object. Essentially, it's a single source DIA object. But it's very important for transient science to know what the limiting magnitudes recently were in that area. And so it's a little bit too time consuming to go back, and within that 60 seconds, we can't go do forced photometry over the last 30 days. But what we can have ready is the limiting magnitude of any images that overlapped at that area. So that's what you get as your like recent limits in an alert for a new source. And then within 24 hours, we can go back and do that forced photometry for the last 30 days. And then, so if you have one night, it's a new DIA source, it goes out as an alert, and you get the limiting magnitudes from the past 30 days. If you see it again sort of the next night, then that new alert that comes out for that same DIA object, now you have the 30 days of forced photometry as well. So that's how we're getting you the forced photometry. Pre-covery is also the word used there. That's how you will have access to that as fast as possible. And then, of course, in the alerts, the last thing on the list there is the image stamps. So it's the difference image and the template are what you get, because you can reconstruct the direct image from those two things. And for each of the images, it's flux variance and a mask plane. And the size of those stamps they're never smaller than 30 by 30 pixels, which I think is like 6 by 6 arc seconds. But if it happens to be, if the footprint happens to be longer, so for example, like trailed sources, then I think the stamp is going to be larger as well. You want to like have the stamp at least be the size of the footprint. So that's what's in the alert packet contents. From here, I go into a bunch of FAQs. So may I pause for questions now, just because that was a lot of info. So I'm happy to take questions before continuing.
Charles Liu has a question in Google Doc. Would you like to ask your question?
Who?
Charles Liu?
Yeah. Can I be heard?
Yes.
Yeah. Just wanted to confirm that the 24-hour cycle and the 1-year cycle products are independent of the 60-second alerts, right? If we're not quite down to 60 seconds in 2024, the stuff will still come out every day. Is that right?
Yes, if we don't get the AP production down to 60 seconds, everything else I think stays the same. It's just it'll be 120 seconds or wherever it lands.
Okay.
Yeah.
I figured that was the case, but I just thought I would confirm. There's no coupling of the different time scales. Thank you.
I don't think so. And I don't think, as far as I know, it's not on the table to cut any of this to get down to 60 seconds either, because most of what we're putting in the alert we pretty much figure is essential. So I'm not sure if that was your question, but I don't think that's on the table.
Yes, that's exactly the. Yes, thank you so much.
Okay. Yeah. Come up and. They'll hear you online.
Okay.
Yeah.
So I was curious whether does this work? Okay.
You won't hear, but they hear you. Yeah.
I was curious whether there's any idea to have a force photometry service that would go longer, like that you could request and retrieve the force photometry. Thanks.
Yeah. So for force photometry, for anything that's been detected, you can leave it on because there's more questions. Yeah. For anything that's been detected, we'll continue to do force photometry. I think it's for 12 months. That we continue to do that force photometry. Alerts don't come out if the thing has faded below signal to noise ratio of 5, but the force photometry will continue. So you can query the prompt products database to get that force photometry for your object. And then, does that answer your question fully? Or is your question more about can users, okay, I'll extend your question. So there's also the science use case where some people want us to do force photometry always at these locations on the sky, whether or not we detect something. And that's definitely on the table. And right now we're figuring out the process for making that list of coordinates. Yeah.
I think it was like more.
Yeah.
I think it was also like a force photometry request service. So an API where one could submit an array and deck and then get force photometry on demand at that location. And I don't know if that's doable or through the RSP or how you might do that.
Yeah, that's absolutely doable through the Rubin Science platform. So you would log in, you'd probably be logging in, I think now, if you log into the notebook aspect and you would use the LSST Science Pipelines force photometry, you'd give it your own coordinates and it could do it for you. That's how it is now. Whether we could do that through API, I'm actually not sure at this point, but some capability will exist for, yeah, absolutely.
Nevin, did you have a question?
If you don't mind, you can pick it up too and hold it, or yeah.
Sit here.
Okay.
I just want to make sure I understand the alert packet contents. So a DIA object can contain multiple DIA sources, and a DIA source might be a supernova, and a DIA object, for example, could be a host galaxy.
Not quite. Not quite. So a DIA source would be a detection of the supernova. The DIA object would be all of the detections of the supernova.
Oh, okay.
Yeah, so object is like that point on the sky, and then the source is all the individual detections. So you could think of it as points on the light curve. Yeah.
Got it. Thank you.
And then the object is the host galaxy.
Without DIA in front of it.
Without DIA in front of it.
Okay.
Yeah. Yes.
Let's see.
Clear as mud. Yes.
It makes sense now. Thank you.
Okay. Don't humor me. You can say if it doesn't make sense.
It does.
Okay. Yeah. Come on.
So for the DIA forced source, would we compute the same time series features for the DIA object as well, or would those be separate?
So for time series features, that will be calculated and go in the DIA object. I'm assuming they're going to use DIA forced source because you want to use all the
For
information.
variable stars, I think it would be very useful. But
Yeah.
would there be an overlap in the computation, or is it going to be mostly or mainly the force source?
That's That's a question I can't quite answer yet. I think mostly we want to use force source
Yeah.
wherever possible. That's the one you want to be using because
Yeah.
it's got more information. What I also didn't measure or didn't mention is the DIA object and the DIA source as well. It has not just the difference image flux, but also the direct image flux. So for variable sources, that's even more what you want.
Right.
It's the direct image flux over time. And so, so exactly what time series features this is actually an FAQ, is not determined yet, but some of them should be using direct image fluxes instead of difference image fluxes for variable stars. Yeah.
Cool. Thank you.
Yes, it's a good question. Thanks. Douglas. And then it's the bottom one. Yeah. Press and hold. You'll get it. You really have to just be like, I want.
Oh, magic touch. What was my question? How do you use the button? No. Is there are there any variations of these alerts available for DP 0.1 or 0.2?
No, not yet. No alerts got made, but I feel like I saw alerts from DC2 go by in someone's talk.
We have some simulated alerts from DC2 light.
Oh, sorry. Yep.
We do have some simulated alerts from DC2 light curves,
Mm-hmm.
but a much more useful data set is just ELAsTiC itself,
Mm-hmm.
which has all of the alerts streaming to you with the right format for the most part.
Yeah.
Okay, thanks.
Yeah. Here, you can use this one.
I was wondering if you could say, and it's maybe a little bit into the weeds, a little bit more about this limiting magnitude calculation you were saying. Is that, per whole object, how is this done per band, I presume?
Yeah, the signal to noise ratio greater than 5 in a band, and that's the detection influx in the difference image. Yeah, exactly. Yeah. Okay, any more data products related questions?
Can I add a comment and a question? So on your next slide, you had features in that we haven't included them in ELAsTiC because we don't know how to compute them. There's no information, for example, on when LOMS-Cargill features are computed, after how many detections, etc. So that's missing. But do we have any more guidance on when those decisions on features will be made?
I'm just thinking, I don't know when we're going to decide on that. I know, hold on. Yeah, second FAQ there about derived variability parameters. It's ls.sc/data management tech note 118 is sort of the current thinking of everything we could do. Yeah. So that's actually a question for Eric because he's leading that, and I'm not sure what our time scale is. Yeah.
The other thing that you might be super interested in is we added in some features that you don't have in the alerts, in particular PhotoZ PDFs. And a lot of brokers and classifier teams here will almost certainly want that information. But that is not in the DPDD anywhere as a thing that's going to be provided by LSST. And even if CMNN is loved, that's good enough, I think.
Okay. Yeah. So it won't be in the alerts. PhotoZs don't go in the alert packet. So we'll just jump around our FAQs. So, right. The photometric redshift goes in the object catalog, which is proprietary. So we can't put the PhotoZ in the alert packet. But what will go in the alert packet is some host association. So let me first draw your attention to the first FAQ about host association. So within the alert packet, we'll give you, so host association gets done as part of that 60 seconds. What goes in the alert packet are the LSST object IDs for the 3 nearest stars, the 3 nearest galaxies, just by on-sky distance. Also, the 3 nearest extended objects in a separation distance that takes into account the size of that extended object. It's kind of like still to be determined exactly which association code we use to do that, that distance. And then also the nearest low redshift galaxy. So we'll have a list of low redshift galaxies, and they'll just always have the nearest one in it, just in case it's like a low redshift transient. So with the object IDs for those nearby things, you can then query the object table and get the PhotoZs. And they will have, the PhotoZ data products do include like point estimate and uncertainty, but also the full posteriors. And so brokers are really anyone, any data rights holder is free to use those PhotoZs. So that's how we're expecting brokers to use this host association data, get the PhotoZ data, and use it.
I'll just point out that that means 7 separate calls from different brokers with the same database to all retrieve the same pieces of information, when it could go just the one time in even a proprietary little packet in a topic that only the brokers knew about.
Interesting.
It's a simpler solution in many ways.
Yeah, actually, this is the first time I'm hearing of like a proprietary packet.
Just create a topic name that only the brokers know about.
Have you brought this up with me? Okay.
Hi, my name is Gautam Narayan. Give me a chat.
Yeah. So this is an idea I haven't heard yet. And this is also something I'm not super clear exactly how hard this is for brokers. If it's quite hard, we don't want to impede science. Okay, let's talk further about trying to solve this issue, because I haven't pushed too hard on it yet. Okay. So we've covered host association. We've covered that you'll have the object IDs and you can retrieve host galaxy data. We covered PhotoZs. Should I continue with my FAQs?
It'd be great if you could real quickly say postage stamps, but before you do that, Alex Maltz, is there a question?
There's a question from Natasha Abrams in the Google Doc. Please ask your question if you can. Read it.
Sure. I think this might be in the FAQ as she's been flipping by, but I just wanted to know how many nights of data will be able to access at one time that are associated with an alert. Right. I guess the alert itself is only one data point, right? But how many nights?
Yep. So the alert itself gets triggered on one data point, but you'll always get a 12-month history.
Well, I see. And then in the yearly releases, we will be able to access all the entire data set associated with that data point?
Exactly. Yep. The annual release, you'll have the full, however many years we are into the survey, you have that many years of a light curve.
Okay, thank you.
Okay.
And then Alex, are there any more in the chat?
Not that I see at the moment. Oh, Tom Laredo has a question just now.
So Tom, if you're able, feel free to unmute and ask your question.
If not, I will read it out loud. Regarding including object IDs, will those be available before DR1? Are they produced as the survey goes for the 24-hour data? Will PhotoZs be available for those before DR1?
No, those can't be available before DR1 because we need that object catalog. Yep, it's a good question.
Okay, if there are no more questions for now, feel free to continue on with.
Okay, I'm going to go straight to the question FAQ you requested, which was, would brokers be able to retrieve a larger postage stamp because that 30 by 30 pixels doesn't get you the full host galaxy? And the answer to that is yes, you can retrieve them. For example, from the DeepCoAD from the most recent data release, that's probably the easiest thing to use. There will be an image cutout service. There's a prototype of that ready actually now even that we're using, starting to use with DP0. I haven't actually touched it yet and started to see what it's like, but it does exist. And that's for data rights holders, right? Because it's the 2-year proprietary period. That image cutout service As far as I don't know what the maximum is going to be on that, but about the size of a patch or like at least a single CCD. So data rights holders can get those larger stamps of the science and difference images, of the science and difference images, the direct or difference images once they become available to during the prompt time, which we heard earlier today. I think Bob said that's currently at 80 hours. Who was in the multi-messenger? Yeah, it was 80, right? That he said right now? Yeah. And I'll actually just stop there and just take more questions if there are any.
Oh, I had a question, although I'm not sure how to raise my hand.
We can hear you, so go ahead.
When there's a detection, are there any cuts that are made to throw it out, like cosmic rays or artifact near a diffraction spike, or do you just put a flag on it and pass everything through regardless?
Yeah, no, there's definitely something happens there. So there's the signal to noise ratio of 5:1, but then things that are like we can characterize as artifacts don't go in the alert stream. So that's things like cosmic rays. What I don't remember is exactly how it gets done. Maybe that's still in development, but we definitely aren't going to be passing out things we know are junk, basically. Yeah.
Then there was one more question here in person.
Yes. So the brokers only deliver to people who have data rights, or okay.
No, so the alerts go to the brokers, to the 7 sort of selected brokers, and then they are free to have users from wherever because the alerts themselves are world public.
Okay.
So it's up to the brokers to have their own users. Yeah.
Okay.
So the question you asked got earlier about host galaxy identifiers during the first year of operations is a little worrying. So is there no host information at all in the first year? Because you must be assigning identifiers anyway for objects.
So, right. So I think the early science session is happening now. And so there will be some sort of incremental template built as we go. And I think there will be, it makes sense to have incremental object catalog also as we go, but I'm not the one who can sort of promise it. So we should just follow up and make sure that's, but even if that does, I still don't think there'll be photoses.
Yeah, no, I think that's fine in year 1 of operations, but longer term, this will be a sticky issue.
Yeah, but an incremental object catalog sounds doable to me, but we should check with our early science people, with Leanne, basically. Yeah.
All right. Okay. We want to save a little bit of time for brokers, so let's give Melissa a round of applause again. All right, and next, okay, so obviously a big infrastructure pipeline. We start off with our kind of underlying SCP model of transient host galaxy. Rick talked about that. Then we pipe them into alerts using, to the best of our ability, the information provided from LSST AP about what's going to be available in alerts. And then all that information goes out into broker systems that are tasked with processing this data deluge and doing meaningful science with it. So to hear a little bit about how that gets done, Anais Moeller is going to talk about the Think broker and its science goals. So whenever you're ready, let me stop sharing. Yep. All right. Feel free to share screen, Anais.
Perfect. Hopefully this works. Can you see my slides?
Yep.
Excellent. Hello, everybody. My name is Anais Moeller. I work with Think. And today I'm going to tell you a little bit of the ELAsTiCC challenge seen from the broker side. Before I start, I would like to acknowledge the traditional owners of the land where I work. I actually am in Australia, so I acknowledge the Wurundjeri people of the Kulin Nation. And I'm going to talk a little bit about the work we have been doing in Think. So this is not only myself, but a team of people trying to tackle the ELAsTiCC challenge. So for us, from the broker side, we have two main challenges. There is the infrastructure challenge, which is basically connecting all these alerts that we're going to receive, receiving them and sending them back, enriched, selected, etc., a little bit to mimic what will happen with Rubin and to test data volumes, the latency, etc. The Elastic team has split it in two phases. So we are right now in phase 1, and we will be in phase 2 later in the year. The second challenge that we see, and I'm going to discuss a little bit about some preliminary stuff we have been working on, is classification. So when we talk about classification, this can be a complicated term, I think, because some people think it's just machine learning scores or a probability of this object being that, and other people think it's basically a filter sample, which are two things that could be the same, but are not necessarily the same. So I think I'm going to tell you a little bit about those differences as well, because I think it's very important that we start thinking about them. Now, of course, the brokers, we are not just one. This is the list of full stream brokers selected by the Rubin project. These include people that are right now in the room with you and online. I'm going to tell you the perspective from Think, because that's where I work. That doesn't mean that the other brokers are not doing amazing jobs and doing different things with Elastic. Now, what is Think? Think is not an acronym, which is incredible, I know. It's a community-driven effort, so we want to touch as many science cases as we can. So it's open to everyone. As we heard from the questions in the previous talk, brokers will receive public data and will transmit that public data to the world. So we are as transparent as we can. So we have open source code, etc., and you can get the data publicly without being part of Rubin. Now, of course, having data rights gives you other benefits that we have heard from Melissa's products, slides on products, but the idea is that the broker can touch any community that is interested. We're a team of around 40 researchers and engineers, around 7 countries and growing. And on the top right, I put actually a picture of our first collaboration meeting, which we finally did this year due to COVID and other things that have happened. We designed Think for Rubin. So from the start, we have been working with big data technology like distributed computation. And since 2019, we're processing CTF2 data, just the public part. So that's already available in our webpage. Below, I put a link to the paper with our first publication. If you have questions about the architecture of Think and science cases, I'm not going to get into that exactly. We have a lot of science cases that I'm not going to talk at all today. So if I don't mention your science case, that doesn't mean that the broker is not doing or cannot do it. So I will summarize what we do as enrich, select, and distribute to maximize science. And when we talk about these things, I'm going to start a little bit in the other way around. I'm going to start with distribute, because how do you distribute? Let's say you get the CTF or Rubin data. We enrich it, we select it, we do all this magic in the brokers, and we distribute them. So there are 2 ways that the brokers can distribute data. One of them, it's to trigger follow-up, like, for example, a real-time API. That's what we have. It can be a Kafka stream. It can be like a Slack bot. It can be whatever you want that is automatically triggering a follow-up or a reaction. But it can also be a little bit like a human-based thing, like a web portal or a REST API, so you can query the database and do your science analysis from home, from your computer or at work. So this is how it's structured for the production mode, which is using data from the surveys. For Elastic, it's a little bit different in the sense that we are testing the infrastructure, the part 1. We are getting this 10% of the sample that was previously mentioned in the brokers, like in the loop. And we process it, we ingest it, and then we return it back. So what we have been doing is, we are receiving this 10% of the sample. We have adapted Think for LSST filters, the fields of the alerts, because they're a little bit different from, for example, CTF. So these are little infrastructure details, but they're important to tackle. And we have also resent the stream back with fake classifications. If you can see on the right, this is an example of what we sent back at one point. You can see that we have alert ID, when we ingested the alert, what version are we running, and you can see the classifications. And you can see the classifier params that is coucou. Coucou is in French, hello. So that tells you that our infrastructure engineer is French. So we have a little bit of French in our parameters back. But this means that it's right now just a dummy classification. We're not sending true classifications back. And I think this is the next step of the Elastic Challenge. And I think it's a very interesting sample to work on to see what we can do with Rubin. Now, with the Elastic Challenge, and in particular the simulations that Rick told us a little bit before about, we want to see how we can enrich them and select them. In real life, what happens is that we get that data from a survey. We first do a real bogus quality cuts, basically, and the information that Melissa was telling us just before in the talk. And then we start enriching it with information from things like catalogs, like cross-matching coordinates, trying to cross-match footprints, using like VOE events, GCN notices, for very fast transients, maybe like a gravitational wave detection, maybe a GRB detection. And we also compute like features. Let's say that you have a light curve. Is it rising? Is it fading away? Is it red? Is it blue, etc.? This is how we do it in real life, that together with machine learning classifiers to provide scores of these objects being potentially a supernova or potentially a microlensing event. Now, we have a big machine learning background. In particular, I like you can see that we have different algorithms going from supernova classification to microlensing, fast transients, and we are now implementing some new ones, which uses multiclass. I think one of the things I would love to discuss is the difference between just thinking of the machine learning classifiers providing this score and actually selecting a sample. What we do is that we get this information, and then people can select what is their threshold for scores plus cuts, for example, with cross-match of catalogs and other information. Is it red? Is it rising? And then you can get like a filter stream and get your information of the candidates that you're actually searching for. In Elastic, we don't have this. So there is some contextual information, which is very valuable. But I think this is something that we need to think about when we move to Rubin. Elastic is super important to understand how machine learning classifiers are working, how our infrastructure is working. But as we move forward, we also need to think about the bigger picture as well. Now, we got the training set for the classifiers, which Rick mentioned before. On the right, I'm putting the taxonomy of the classes that we have. There are some big taxonomies like supernova, like fast, long, recurring, and then you have the little classes below. I think it's important to know that from the broker side, this taxonomy will impact the classification performances. In the sense, some classifiers are more targeted to one type of object than other, or maybe a broader class or a smaller class. So from the broker side, it's important to notice. Also, the size and balance of the subclasses can affect the potential performance of machine learning algorithms. I'm not talking here whether you can do data augmentation or not. It's, let's take just the raw training data and train our algorithms. Can we perform competitively? Because it's well known that some algorithms will perform better with very large data sets because they don't get feature extraction like recurrent neural networks. But if you get a random forest with a feature extraction like a fit over the light curve, then you can get better performances with a smaller training set. So you need to balance all that when you're working with a broker. The other thing that we have been, and I will mention this a little bit more, is baselines. What do I mean by baselines? This is the history. So we know that we will get this history in the alerts of 1 year before the object was detected, and the 30 days that were mentioned for the first photometry, the second detection. But when we get a training set, we get like basically the full span. So do you use the whole thing to train because maybe you don't have all this information? Do you make cuts, etc.? And this is linked to what I put below, which is magnitude limits and detections. Now, this is a lot of words. I think the next thing is more interesting, is just an example of some of the likers. These are likers that we plotted different ways, so don't worry, the different styles from the elastic training set. And you can see we have some very nice type 1a supernova, we have some stars, but then you have type 1a supernova that basically have 5 epochs with huge gaps in between. SN1BC, and you can see here on the top right, I don't know if you can see my mouse, but I plotted like a line where it's the peak supposed to be of that 1BC. And you can see, well, this is potentially a supernova, but then you have all this potential noise or something else down here, which is a good question. Do we use that to train? Is it just like noise? And this is something that we need to think in the real life. We have a lot of noise. Can we mimic it? How big are the likers that we need to use? So I am now going to go through some of the machine learning tests that we have been doing for Elastic with Think. This is all very, very preliminary. So whatever I tell you is not necessarily the end game, but to give you an idea of what type of algorithms are we using, what challenges do we have, etc. So this is a classifier that we have right now in production with CTF that is finding early type 1a supernova with active learning. So the idea is the following. We want to find rising events, basically. So we want to find things that are rising, that look like type 1a supernova. We do some type of filter extraction that you can see here on the left. For each filter observations, we actually fit a sigmoid and try to see if this object is rising. We make a cut to only get this rising object. One of the challenges we have found when we were dealing with the training set is that some of the events were way too faint. And that was producing a problem with the sigmoid fit. So we had to raise a little bit the bar of the signal to noise. So this is something that is important to know. Like some algorithms are not tasked for very, very faint things. So we had to put that at least one filter had a flux cal, which is it's a flux normal that comes with a 0 point of 27.5, if I recall correctly, bigger than 100. So this is one of the limitations right now of these plots that I'm showing you. We're trying to see what we can do to improve it. But to tell you a little bit about the active learning idea is the following. We know that we don't have complete training sets of supernova and other types of transients and variables. So what we do is we get a machine learning classifier in a loop, basically selecting the objects that we would like to have a tag or have a spectroscopic follow-up, and you train it that way, improving every time your classifier. So right now, because it's all simulations, this is not real life. But you can do this thinking that we can trigger follow-up with like Formos or any other telescope. So this is an example a little bit of how fast the training goes. We're talking about 60 loops here. And you get, actually in blue is the active learning loop, in orange is the randomly high purity very quickly with the active learning algorithm. So our idea here is to first get a classifier, so that's coding it at the end, but also test the idea that we can give a list of potential things to follow up, so we can get better training sets for the future. So this is work led by Marco Leoni and Emily Ishida, and they have done the plots. This is all very preliminary, but to give you a sense what we are trying out. Another thing that we're trying is a new algorithm that it's shown here. Is an LSTM deep network. We're using multi-class classification, so you can see the confusion matrix to the right. This is work led by our Brazilian colleagues and Argentinian. So we have, you can see that the classification accuracies can be high for some of the subtypes, like flares or dwarf nova, but it's getting harder and harder for the supernova. And one of the questions here is why? Because a lot of classifiers have been developed for supernova. And I think I'm gonna tell you a little bit about that in the next slide. But this is something that we're trying as well. How can we do a multi-class classification? So this is the supernova side. So this is an algorithm that we are using as well for Type 1a supernova cosmology in the dark energy survey. It's also implemented in Think and in production right now with CTF. It has been adapted to elastic inputs and filters. One of the challenges here is the training set curation, because these very long baselines that I was mentioning to you, like all these limited magnitudes, not exactly what we get all the time with the brokers. So for example, if I want to do a training set where I randomly cut parts of the light curve and try to train with that, if I don't have signal, that doesn't make any sense to train with that. The other thing is sampling. Do we really want to train with things that have only 3 points for the light curve, for example, for a supernova? 3 points is completely reasonable for like a flare or something like that. But something that is long, is it good enough? So I did a very quick test before yesterday, trying to do some accuracies of Type 1a versus non-1a classification, and you can get like 75% accuracies, which when you compare it to what we're doing, for example, for cosmology in the dark energy survey, where we have less than 2% contamination, this is not that great. Now, what happens with the dark energy survey, and this is where I want to put an emphasis thinking about the future once we finish ELAsTiC, is that we're also using selection cuts to get like a very pure sample. So one of the questions here is, are we aiming with ELAsTiC to test capabilities of triggering follow-up to complete light curves, or are we just finding the best light curves or the best events to do the astrophysics? So that's a question I would like to launch the discussion a little bit with, and because I knew I was at the end of the presentation, I wanted to start asking some of these questions as well to you that you are hearing this. So I think in summary, we're doing the ELAsTiC infrastructure tests are ongoing, are working fine. Thanks to the team that have been doing this, including Rubin, that we have been interacting a lot. We are in the machine learning scoring phase. I think one of the important things is the training set curation is non-trivial. I think that we forget sometimes that when we are going to use real data, we're potentially going to mix different scores of machine learning classifiers, plus selection cuts, using catalogs, using context, etc., to get the samples that we want, the filter samples. And this also introduces a challenge, because different machine learning algorithms have different ways of scoring things, multi-class, binary classes, etc. How do we combine them to something that is just one thing? It's not trivial. The 3 questions I wanted to ask a little bit to the public to spark a little bit this is, what are we aiming for once we are trying to do Rubin? Because we can do a lot of things with ELAsTiC. Shall we aim to try to identify very good quality photometrically classified samples to do, for example, Type 1a supernova cosmology? Or do we want to get very sparse light curves very early so we can actually trigger follow-up to complete those light curves, in particular for things that are short-lived? Now, I know variable stars, you can have very long baselines and actually do these. There are challenges for different fields, but I think this is important to ask ourselves, what can we extract a little bit more from Elastic that is not just having a score and this is it, or just stress testing the infrastructure. So this is my last slide. I'm more than happy to answer questions or continue asking questions to everybody about what else can we do with Elastic. But it's a great test set, I think, that we will be very, very useful to prepare for Rubin and the starts of operations.
Questions either online or in person for Anais?
Hi, I was just wondering why there are 7 brokers. Are they doing different things? Could there be a benefit to merging into just one?
So the decision why they selected 7 and not 1, I am not gonna answer that because that's a project. But what I can answer is that we are all working in different things, but we have some intersection. So I think all of us are touching one way or the other supernovae, but maybe with different communities. So our goal, our infrastructure, the way that we design the machine learning classifier, the filters is different. So I think the advantage of having different brokers is that we can target different things in the community. We have a huge amount of data coming in, a huge community that will take advantage of this data. Why not search what broker can actually fit better your science case and modify it for your science case, because we are all in different ways of thinking and constructing. I think that's an advantage, not a disadvantage. I also think that although 7 sounds like we are competing all the time, we are actually quite collaborative. We talk a lot between each other. So we have some intersections between what we're developing. For example, the European brokers, Fink, LSST, and Ample, we have been discussing about potential platforms where we can save some joint data and share data. LSST is using Fink machine learning scores for supernova. Fink will potentially use some of the cross-matching that they do with host galaxies from LSST. So you see that it's not like LSST, we talk a lot about infrastructure together. So it's a very vibrant community, I think. And I think we should embrace the diversity that having 7 different brokers provides. Yeah.
So Anais gave you like the perfectly politically correct answer, but I think the right answer is there are 5 separate funding agencies and 7 separate groups that wanted money.
That's another interpretation. I rather think that diversity is a great one.
Other questions for Anais? Please go ahead.
Hi, I was wondering if you could talk a little bit more about the initial filtering phases in the broker, such as like asteroid identification or like WISE catalog cross-match or things that would separate transients from non-transients. Thanks.
Yes. So I didn't talk about this at all. You're absolutely right. I even don't have a slide about this. No, I don't have any. So when we get the alerts, Rubin, CKF, we basically do this real bogus quality cut, basically. And then the rest of the stream gets sent to enrichment, okay? Now, enrichment includes all the alerts that pass these quality cuts get enriched. At this point, we are not cutting anything. So you will have the cross-match with catalogs. This can be MPC, like Minor Planet Catalog, and this could be footprints of gravitational waves. This can be machine learning scores, whatever you want. Once we have all this enrichment, we start selecting things. And this can be a hierarchical thing or a parallel thing, because you have all this information. So, for example, right now we select using Minor Planet Catalog, we select some asteroids, but we also have other mechanisms to select asteroid candidates using color information, using tracks, etc. So this can be done first, and then from the rest of this, you can get your potential transients and variables, and then you can filter, for example, all the variables that are known or things that have very long baselines, and then you can get your filter stream. So this can be hierarchical. However, because all the data has the information, you could do it also in parallel. You can have things that are both a potential, I don't know, a variable star, an AGN. This happens a lot actually. An AGN that is rising in the light curve and a supernova candidate. And you can, because if you do very loose cuts, you can have them both. Because if you want very high, for example, not missing any of them. But this is not necessarily hierarchical. It depends on the science case. It depends on the person because this is highly customizable. I don't know if this answers completely your question because it's very depends on the science case and the group that wants to have this selection. We don't veto for you. If you want a predefined filter, we can show, like we already have some of them. And for example, for the supernova, I can tell you we eliminate asteroids. We eliminate things that are cataloged like variable stars in other catalogs, etc. And then we make a selection of things that haven't been detected before, or at least not in the last 2 years. And then we make a selection with the machine learning scores using 3 machine learning scores, actually. So that's hierarchical.
Great, thanks, Anais. It's 5 p.m. now. I did see a question in the audience, but let's see. Maybe if there's anybody on, sure, if there's anyone on Blue Jeans who maybe has any questions, maybe they could take the last one and afterwards we could chat. And if not, feel free to go ahead.
A very quick question. I wonder if there's any photometric classificator already pre-trained so that we can use it with external dataset, just providing light curves as input.
Yes, so the abundance of machine learning classifier pre-trained is very big. So there is a lot out there. The question is whether we can use it with Rubin data. So some of them are filter agnostic classifiers. There's a couple that I know from the top of my head, including like Scone and very recently Umar published one, which I don't recall the name. So that could be directly applied to the light curves that we have in ELAsTiCC, for example. Now, would that give you a high like a high accuracy or a high performance? It's not very clear because it will also depend if it's robust to different observing strategies. So that this is a very important thing or not. So I think there are classifiers out there pre-trained, but not necessarily we can easily apply them to Rubin. Now that doesn't mean that they cannot be adapted to be using Rubin data, with Rubin data.
Great. All right. We're at 5:02, so let's close out the session there. Let's thank Anais again. And I just wanted to take a second to thank all of the people who are working on all of these individual pieces to enable time domain astrophysics with Rubin. It's really exciting to see all of this come together. And in the audience, if you saw any of these pieces and alarm bells went off and you thought, I'm trying to do a particular type of science and this is a barrier to that, or maybe I could improve upon the way things are currently being done for my use case, please get in touch. Feedback is absolutely wonderful, especially since we still have a tiny bit of time to make modifications before Rubin. So thanks, everybody, and enjoy the rest of your evening.